hardly interested in. So today we will have 5 talks, and the first one is of Vladimir Temlyakov, and he will talk about smooth fixed volume discrepancy, dispersion, and related problems. And yeah, all the other talks can be found on the website, so please have a look. Volodya, stage is yours.
Okay. Thank you, Maria. My talk will be a rather introductory one. So I will try, as you can see this from the title, I will try to tie together these concepts and how they are related. But before I introduce the concept of smooth fixed volume discrepancy, I will describe discrepancy in general, because clearly many of us, the majority of us, know those concepts, but not everybody. So for those who do not know this, I will make this kind of introduction. So let's proceed. So all these things like discrepancy and related things could be seen as a numerical integration. So this concept is very well known to everybody, so just more like notational thing. So we denote the cubature formula with given points, knots, and given weights this way. So we evaluate function at this point and then make the sum, and we try to approximate this integral by the corresponding cubature formula. And terminologically, we say that it is a cubature formula if we are talking about multivariate functions, and we call this quadrature formula if we are talking about univariate functions. So that the two important ingredients here are the points and the weights. So this is the most kind of general cubature formula out of those which we are going to consider. In some special cases which are of great interest, when all the weights are the same, which is 1 over m, then we call these cubature formulas quasi-Monte Carlo cubature formulas. I mean, this is special case, but this case is of interest. For instance, the discrepancy will be the one which has the weights 1 over n. So now the question is, and this is what is goal, if for a given class, function class W, we want to find this cubature formula which is good for every function in this class, then we certainly need to solve this optimization problem. So first we introduce the worst error for the numerical integration of functions in this class. So we take supremum over all the functions in this class. And next step will be take infimum over all lambda and xi, but before we proceed to that step, let me make the following comment. If this W, and this is important comment because again, it translates into the discrepancy setting. So it may happen that the function class W, which we are talking about, it is parameterized with some y, and these are points from the set. And on this set, we can introduce the measure. So if you have that, then basically the supremum, it could be seen, I mean, this, roughly speaking, as L infinity norm with respect to that measure on this set. But if you have these parameters, that means this quantity depends on parameter y, on this variable y, then we can consider other norms too. And this allows us to introduce what is called the average case setting. And this is again the most general formulation here, because we can consider now vector p, and it makes sense, we will see later. So for this vector p, we introduce, instead of supremum, which I mentioned that could be seen like L infinity norm, we can introduce LP norm. So this will be, instead of supremum, it will be the norm with respect to this parameter y of this error, So, and this is the remark how we understand this measure. We can understand this measure in different way, but the Lebesgue measure is a convenient one. So now optimal error, which I already mentioned. So we now optimize this quantity. Either for p equals infinity, it is supremum, it is a classical, the worst case error. This is a classical error for the cubature formulas. And this is more general LP norm, but now we minimize over all the weights and all the points. Certainly, if we are talking about special Kubicev formulas, when all the weights are the same, which are 1 over m, then infimum is taken only over these points. I should say right here this comment that even if you can estimate these quantities, clearly the problem of finding these points which provide optimal or almost optimal or optimal in the sense of order is, especially in a multivariate case, it is a really tough problem. So this is, with weights it's kind of easier, but as to points, this is a really difficult problem. So now examples, and this is, we are making step, and again, in the multivariate case, there are many different classes. And in multivariate situation, in some cases, the problems are still open. You do not know even the right order of those quantities. But now we will make step to the concept of discrepancy. A discrepancy can be seen as a special case of numerical integration. Special in the sense that we consider a very special class. And this class will be defined momentarily. So this is a definition. This is a standard definition for a characteristic function, univariate, and this is interval, special interval from 0 to a. A is just a number. In our case, it will be a number between 0 and 1. So we will live in unit cube in multivariate case. So this is enough for us. And multivariate function is defined as a product, but again, it's kind of special. It has the very left vertex in 0. And the moving vertex is this, A. It points AJ. AJ is the J's coordinate of this vertex. So this is like a parallel pipette with the very left vertex in the origin. And this is the whole class. This is the whole class. So as you can see from this definition, this class exactly falls in that category, which I described like a class which is parameterized by something. And this something here is a point from the cube 0, 1 to the d, and certainly on this cube we can introduce any measure, and we can introduce a LP norm of that error. So, and this is what we do. So the classical concept of discrepancy, sometimes it is called star discrepancy. It is just a supremum, or we write maximum here because in this case it's clear that it is achieved. So we are writing in this way. So this is the classical concept. And this concept clearly coincides into the previous notations, coincides with those the upper bound, the worst error of numerical integration for the whole class, for this class, chi-d. And in other notation, this is lambda m, where lambda is a Kubicev formula with equal weights 1 over n. So this again, just look at this notation. So this is x, this is the set of points. And m is the number of points there, so clearly x, we don't, it kind of duplicates, but anyway, and d is the dimension. And the norm in which we measure the error is given here. Well, now some historical remarks. I'm pretty sure that everybody knows that, but anyway, just to pay tribute to people who contributed in that, let me just mention that. The first result, not maybe result, the first thing which attracted attention to this problem, what the conjecture which was formulated by van der Waerden long ago in 1935. Now this is the conjecture, and that was in the univariate case, but it turned out later that the univariate case, when this sequence is given. Not the points, which we can optimize the points depending on the class for any fixed m. But in this case, the setting is a little different. You take a sequence. So now sequence is given. And now for elements of the sequence, we calculate this quantity. And the conjecture of van der Waerden was that this cannot be of order 1 over n. So it should grow. So that was a conjecture. And it turned out that, yes, indeed, this conjecture is correct. And this was proved by van Aarden Ehrenfest in 1945. And she proved that not only proved that it is equal to infinity, but she guaranteed some rate of growth to infinity. So basically, iterated log, double log divided by iterated log, triple log. But this was the very first result in this direction. And now let's list some more results which are closer to us and closer to optimal results. So, and for that purpose, let's introduce the quantity like this. So infimum, this corresponds to optimal cubature formula. So now we are optimizing over C, over the set of points. But as I already pointed out, there is no waste here. So the only thing which we can optimize is the point set. So in other words, how to distribute these points in the unit cube? One can say this would be kind of uniform, but in this sense, the most uniform distribution of these points. So this is what we do. And these are the known results. The first result, which basically started the whole this discrepancy theory direction, was a result by Klaus Roth in 1954. And he proved the lower bound for any dimension G, the lower bound like this. And later it turned out that this is the right bound. So the upper bound coincided in the sense of order, coincided with this one. So I want to attract your attention to this m to the negative 1. So when we have things like this, like integrating characteristic functions, the smoothness in L1 is 1. So, and it is clear that we can expect to have something like this, m to the negative 1, and we cannot do better than m to the negative 1. That's for sure. Then you can understand this easily, just dividing this by small cubes, and in one of those there will be no point, so we cannot get better estimate than this. But it turns out that this lower bound says that and this is what is non-trivial here. Now that this is extra log here, so it should grow like this. It should grow like this. If you multiply this by m, it will grow like this log to the d minus 1 over 2. And the further results, let me just list them without any further comments. So it turned out that the case d equals 2 is sort of the easiest one. So in L2, it was the same for all d, and the proof was similar. But in case of L infinity, so this is classical, the most classical one, it turned out that in two-dimensional case, we have this lower bound. And as you can see from here, it is different from the case p equals 2, because in case p equals 2, this would be just 1/2. And here is log n. But it turned out that this case, and I will formulate this as a problem, is still not solved if instead of 2 we put d here. And Wolfgang Schmidt in 1977 he extended the Roth's result to this case, and it is clear if you look at the right hand side, this right hand side does not depend on q, but that means that the lower bound becomes stronger when q goes to 1. But we don't have a result for q equals 1. So it's again an open problem. But for all q strictly greater than 1, this was proved by Schmidt. In case of L1, that was an interesting and very nice result by Halash in 1981, but he proved this. And as you can see here, the right-hand side does not depend on d. So in a sense, he proved this for d equals 2. But we cannot improve this for at least, I mean, it is improved a little bit, but you don't know the final result for L1 norm in the dimension d. So, and here is that problem, which William Chen and Beck, they call this excruciatingly difficult great open problem. And that was formulated in their book in 1987. So basically, the problem is they formulated this as a conjecture. They asked to prove the lower bound like this. By that time, the upper bound like this was already known. So that was the big deal to prove this. It's still unsolved, and some new conjectures appeared, and I will comment on this a little later. And basically over here. So I write recently, but recently, you know, time flies. Now it's not that recently, as you can see, that means 2008. But anyway, there were several very nice papers by Dima Bilek and Michael Lacey, and then by Dima Bilek, Michael Lacey, and Armen Vagarshakyan. And they improved a little bit the error of the lower bound, which is specific for L infinity, because clearly this quantity is greater or equal than this GMD and in L2 norm. And then the Roth's bound would give us this bound, but divided by 2, only this one, without any extra this delta D. And very non-trivial step, and this proof is technically very involved and very non-trivial ideas, allowed them to add this delta D, I mean, this delta dependent D, and actually goes to 0 when D goes to infinity. But anyway, it was a breakthrough result in this direction, which showed that indeed L infinity is different than from L2. And they formulated as a conjecture that here the right order is D over 2. So instead of all these things D over 2, in case of D equals 2, when it is known, both quantities D minus 1 over 2 and D over 2 coincide. Both of them are equal to 1, but for D greater than 2, we don't know. Which conjecture is correct, we don't know. So anyway, so this is a remark, but now let me, before we proceed to this, let me make the following comment. The numerical integration, usually in numerical integration, we are interested in numerical integration of smoothness classes. And typically the univariate or multivariate classes, typically we are interested in finding the right orders of numerical integration for all parameters of smoothness. So that means smoothness 1, 2, or even fractional smoothness. So we are interested in that. And in that case, it is very natural, at least I think it is very natural, to consider the setting for the discrepancy and smooth discrepancy, because that discrepancy which we just discussed, it corresponds to the characteristic functions. And in terms of smoothness, these are classes with smoothness 1 and L1. So why don't we consider more smooth functions? And I will explain this, but then just jumping ahead, I will make the following remark. It turned out that for our applications, it is important that we consider different smoothnesses, because, for instance, we understood, and it's kind of easy to understand, that the discrepancy, or for us even more important, that fixed volume discrepancy is closely connected with dispersion. And in order to get some results for dispersion, it is sufficient to get the corresponding results for this fixed volume R smooth discrepancy for any R, doesn't matter. And it turned out that we can prove some results for R when R is like 2 or greater than 2, but we cannot prove similar results for R equals 1. So it also allows us to make some progress, but should we be stuck with R equals 1 in all cases, that we would not be able to do that. So this is just a remark, but now let's look at this. So now we are introducing the concept of smooth. And next step will be to introduce the concept of fixed volume. So what is R smooth? So again, we will consider something like characteristic functions, but smoother. So this is the whole point. So if you look at this, this is just a characteristic function, and it corresponds to 1, and the 1 is our smoothness. And again, I stress that it is in L1, because it's known that numerical integration is sensitive to smoothness in L1. So and now the next step, you consider just making like a sort of polynomial, making the on this interval, take a convolution of these two and get this kind of spline or B spline. We get this, and if you repeat this iteratively, we will get R smooth in L1 functions, and we support like this. So clearly, every time we take a convolution, support increases by adding this support, and so this grows, but it doesn't matter. R is fixed. So these are functions which have finite support, and they have smoothness R in L1, and this is their support. And now, instead of that class which we discussed, we will consider a little different class with all these smooth head functions in that class. But before, some notations. So it's convenient now to index these functions by the box. And the box has this form. So we just Z is the center of the box, and this is exactly like in the previous slide, the support of this function. So basically, this will be a support of that head function, which is defined on this box. And we define this function as a product. So it is a product of univariate smooth functions, which we defined here. And this is on the box. This is on the box. Now we can see the U, and this is just for convenience. Actually, we can consider U between like 0 and 1/3, between 0 and 1. It basically that doesn't matter. The result do not depend on this bound, but this is convenient to consider that. Then for energy, this is just a remark that all the functions, they have supports in a little bigger cube. But when we will talk about this average case, and this is what we will discuss too, it is more convenient for us to consider a periodic case. And periodization is done in a standard way. So we just take this sum and all the functions have finite support. In our case, it will be finite support. So this is just finite sum, so no question about convergence. So this is our periodization. If we have F, this one is one periodic in each variable, and this is the one. And notationally, as you can see, we have tilde here, or this wave on the top. This means that this is a periodized version of this function. So certainly, if our function has a support in the cube 0, 1, then the periodization on that restricted on that cube coincides with function itself. So now notational thing again. So as I already mentioned, now we consider instead of that class of characteristic functions, we consider this one. And here is also one important thing. If you remember, for those characteristic functions, we considered all the parallel pipets with fixed left vertex. And sometimes it is called that those are anchored at the origin. But now we allow the Z, and this is the center. This is the center. And in that case, the center also moved. But in this case, this Z, the center, it allows to move. And U is the shape of this, allows to change too. And these two kind of independent. So in this case, we have a little bit more freedom. But clearly, you can understand this easily, that if you are talking about L infinity norm, so there's the discrepancy in L infinity, that it doesn't matter. If you allow this left vertex to move or not, it doesn't matter. It will be the same result in the sense of order. But I will not go in that too much. But anyway, I want to stress that now you have two free parameters. Z controls the position of the center, and U, the most important in the sense, it controls the size and the shape of the support of the function, of the smooth function. And now it's time to define this periodic R smooth discrepancy. So it's written like that. So again, very similar to what we did with discrepancy, but some new ingredients here. First of all, now we can define this not only for weights, but also for not only for points, but also for weights. Certainly, we could do this for classical discrepancy too, and that was done. But anyway, so it is here. It is here too. But now we have this Z and U, and see in this case, in this definition, and you put infinity here. We take supremum for all of them. So this is again classical arrow of numerical integration for the whole class, for this whole class. And this whole class depends on two parameters, Z and U, and we take a supremum of all of these parameters, Z and U. So this is classical. So, and this depends on points and depends on weights. But the next step, again, this is clearly parameterized by Z and U, and which are from cubes. Clearly, we can introduce Lebesgue measure on there and define LP norms on there. So, and it is called, you call this LP discrepancy, and R smooth or LP periodic R smooth LP discrepancy Some authors call this Weyl R-smooth LP discrepancy. So this is just, again, terminology, but what is that? That same logic which we already discussed that. So first, we take the norm P1, and this norm is taken with respect to Z. And then we check the norm LP2 with respect to U. So we have two important parameters which play different role. So Z is just a shift, and U controls the shape, the size and the shape of those supports. So clearly U, in a sense, more important parameter. And as I write here, and this is kind of clear, that for P2, the value infinity is the more interesting, because this is just supremum. It would guarantee this error bound for any smooth head function independently on the shape of the support. So that in that sense, it's kind of more interesting. But now let's keep going. Some results. And these are not very new results, but anyway, comparatively recent. So it turns out that in L2, when everything is in L2, that means P1 and P2, both of them are equal to 2, then we know the answer. And it will be a little bit more general. So we know the order. So there are two results. One is the lower bound. So in this lower bound holds for any natural R. So this is, in a sense, you can look at this as a sort of analog of the Claus-Roth result for discrepancy, because that was in L2. So, and this is the bound, and as you can see, the result is very similar. So if R is equal to 1, that it will be exactly like in Roth's bound, and this extend is for any R. But remember that here we also integrate over Z, so which makes this quantity smaller. But anyway, so this is the lower bound. Those are minor things, and it turns out that the known results about curvature formulas give us the upper bound. But now let's look at and compare. So the upper bound for the quantity which is bigger than this one, because one of the norms here, the norm which I pointed out as the most natural for with respect to U, the L infinity norm here, not an L2. So this quantity a priori is bigger than this one. So for sure, this one is greater or equal than one. So, but it could grow faster. But it turns out that not. In this case, there exists. So this one is for any Xi and lambda, but this says that there exists one with this. So if we take a supremum or infimum over this Xi and lambda, then this will be the right order. This one and this one will be the right order. But if so, that means these two results, they solve the problem in the case P1 is equal to 2 and P2 any between 2 and infinity, including 2 and infinity. So that means this closed that one. It was very interesting that in case of R, an even number. So see, now we do not allow R to be 1, because R1 is an odd number. But in this case, we managed to solve this problem much, I would say, deeper. Let me just put these two again, a theorem and a proposition. Theorem gives the lower bound, and that was new this year, but this one is just a corollary from the results for curvature formula. So let's look at these two results and compare. So as you can see, the lower bound is again the same like it was before. And in this case, this somehow should remind us about the lower bound, but it is stronger here because L1 here, not LQ, because this is kind of extension of results of Hallas, but it's clearly much stronger. But R is an even number now. You cannot do the same result which Hallas did for classical discrepancy, but for R even we can do more. We can do this. And it turns out that this is the right order. But what is here? See, P is any strictly between 1 and infinity, and this is with respect to Z. So this is the averaging over shifts, and L1 norm with respect to the shape. And it turns out that the same bound holds for bigger one when with respect to u we take L infinity norm, that is supremum. That means these two results and the bounds, as you can see, are the same. So these two results give the answer in the sense of order with respect to M. In all these results, we don't care about the dependence on D. I know that later we will see today results which are concerned about both dependence on D and M, but in these results, we don't care about that. We just fix D and we are interested. This is more like standard approach from like the beginning of last century and till now. It's the one which is of interest clearly when D is fixed and what is the right order with respect to M. So then these two results solve this problem for P strictly between 1 and infinity. This is P1, and for P2 any between 1 and infinity, including 1 and infinity. So this is basically the end of the story, but this is for even numbers. The upper bound for any R, but the difficult point here is this lower bound. So now let's proceed to see. I already spent almost more than half of my talk talking about these known results, but still I think you got some idea, some understanding what was known, and the most important step, which was comparatively new, I would say, that the step from fixed smoothness R equals 1, what is classical discrepancy is about, to arbitrary smoothness, but in this arbitrary R is still a natural number. Now we can do something like fractional, but now it's not of big interest for us. But now next step. Now we will consider, in addition to that R smooth discrepancy, we will fix the volume. Why is that? And I mean, that was in a sense technical, but it turned out that it is useful in application for dispersion. So what is that? Now we define, and there will be two definitions. This is non-periodic case and similar one will be in periodic case, but here is the idea. So now when we take the supremum, remember we talked about supremum with respect to Z and U, but now we can write this in terms of B, like B is the box where our smooth function is defined. So this is the same. But now, and this is more convenient to write that now we fix this volume. So clearly, if you take now supremum over all this V from between 0 and 1, that it will be the previous definition, because in that case, all B will be allowed. Previous definition in the case of L infinity norm. But we fixed this V. So this parameter, this characteristic begins to depend on a new parameter V. So, and this is the whole point. We can write, oh, it should be R here, not 2. I'm sorry. This is the misprint. This should be R. So now we can also consider not like in classical discrepancy weights 1 over M, but arbitrary lambdas and then optimize over these lambdas. So this is O here means that we are making this optimization over the weights. In the case of periodic, the same definition, and let me read this, and this is kind of in general using this notation. So this is the product of UJ. Basically, this is something similar to the volume. It's not exactly the volume of the support, but something very similar. So if this is fixed, that the volume is fixed. It is clear. So here is the definition. So R is a natural number. Again, this is usual. The volume is like this, but actually even smaller than that, depending on R. But anyway, this is V. P is like this, and this is the definition. So you take this one, the arrow of numerical integration, and here we take 1 over M just for simplicity. And then we take the norm LP with respect to Z. And then take supremum over all U, but under this condition. So if it is no condition like this, that it would be the discrepancy which we considered before with parameters P and infinity. But now we fix this and we get a new parameter here. So this is the fixed volume discrepancy. Let's see. So what is interesting now, we can ask the following question. For some classical known sets of points, we know the behavior of discrepancy. But the question is, how does this V, the new parameter, affect this dependence? Basically, the hope here is that when V is small, clearly when V is big, we cannot expect real improvement over those previous ones. But when V is small, and it's interesting to understand what small means in this case, when V is small, that we can get some improvement. And it turns out that indeed we can get this very small improvement, but it is enough to make a difference. So, and a couple of examples. The first example which we considered, this were Fibonacci points. That means a two-dimensional case, and this is a standard definition of Fibonacci numbers. And this is again a standard definition of Fibonacci point sets. So everything here in the unit cube. And now the question of what is the behavior of this fixed volume discrepancy. But now R is any number, but we can prove the results. As you can see here, R is greater or equal than 2. So we cannot prove similar results for R equals 1. So we can only prove this for R greater or equal than 2. So, and this is the result. So it's written here in the form of numerical integration, but actually in form of the definition, this is exactly that thing. And let me formulate it here, but let's look at this formula. So what does this formula say? So one thing, that this set of Fibonacci points contains the cardinality of this set is exactly Bn. So Bn is the number of points in that set. So that means that this plays the role of m in our previous definitions. So if you look at this formula, we have this Bn to the r in the denominator. So basically, this is m to the minus r. The whole this thing is m to the minus r. This is exactly like we had before. But the extra multiplier here is like this. It is a two-dimensional case. So basically, the exponent here could be seen like d minus 1. It's 1. That's okay. But the log depends on the ratio between V and V naught, where V naught is roughly 1 over Bn. So that means if V gets very close to 1 over Bn, and this is critical, we cannot, it doesn't make sense to go beyond that, because in that case, anyway, the lower bound will be 1 over m, and we cannot do anything better. But when V is of order V naught, this log disappears. It goes into this constant. So that means if V is small, this allows us to get rid of that log. So, and this is the qualitative feature of that, and which was observed first on this Fibonacci numbers, and that was in L infinity. Everything was in L infinity. Then later with Mario, we extended this to this case, and let me just formulate this, the upper bound for that. So if now we take LP norm, but LP norm, remember, in the shifts with respect to Z. Then we can improve that same quantitative observation, that log depends on this product now. So if V is close in a sense of order to 1 over Bn, then it is just a constant. But here, if it is not like that, it is square root. So it's better than in the previous one. In the previous one, the exponent was 1. And here, the exponent is 1/2. And this is for all p between 1 and infinity. Because this corresponds to p equals infinity, the previous one. So and this requires different, somewhat different technique. But anyway, so this is what we did with Mario. And again, we extended this to the case of p equals infinity. So in that case, this is log with exponent 1. And so we did here the periodic case, as you can see. So this is the same as what's in non-periodic case. So let's keep going. But again, let me stress that R here is greater or equal than 2. And this is what I commented before, that in some cases when R is greater, that means greater or equal than 2, we have results for fixed volume smooth discrepancy. But if r is equal to 1, we don't have that. So now these are Korobov-Kubachev formulas. Let me just formulate the setting, because at the next talk, Nasta will talk about this in detail. But anyway, to give a more like full picture, let me just mention, because the question now, we can talk about this quantities like discrepancy or fixed volume discrepancy. And now we're interested in this fixed volume discrepancy because you know that we can apply this to dispersion. And we are interested in these quantities for different kind of points. One problem, very natural one, is kind of to optimize. So extremal case, what are the best bounds from below, and what are the best bounds for that? But also another question is, what are how do these quantities behave for some given well-known sets of points? So one of those is this Korobov-Kubachev formula, so we can say this Korobov sets. And this is kind of generalization of Fibonacci to the d-dimensional case. So this is that. So A is a set of integers, and these are fractional parts. So this is the Kubachev formula. And as it's pointed out here, in a particular case, when A, this vector, is like 1 and Bn minus 1, this is exactly the Fibonacci. So, and let me maybe just keep this notation, and I will not talk about this in detail because I don't have much time. Let me skip this because, again, Nasta will talk about this in details. But anyway, we got in the recent paper with Anastasia Rubtsova, Kostya Rutin, and myself, we proved some results for this periodic fixed volume discrepancy for the Korobov point sets. But anyway, let me skip this and better talk about other points which are of interest, and probably no one else will talk about this. So in d-dimensional case, we know that there are points which are more complicated than Korobov points, but the ones which we know to be optimal for numerical integration for classes with mixed smoothness. And actually, the classes of mixed smoothness very close to discrepancy. So this is also known. And Korobov-Kubachev formulas are good, but usually in upper bounds, we are losing some logs in those bounds. But Korobov points, they give optimal orders. So this is why clearly they are of interest, and we would like to get some results for these points. So what is the definition of that? The definition is not that simple, but for those who know this, it's clearly will be just a repetition. But anyway, it is based on some facts from algebraic number theory. But let's assume this is proved from there. But let's assume that we have that lattice, and A is the matrix which corresponds to that. So, and this is the lattice, and M are the points with integer coordinates, and with these conditions, this condition and this condition. So there exists matter, and this can be proved, as I said, using just algebraic number theory. But if you have a matrix like this, then we can build good Kubachev formulas, and these are those Kubachev formulas. So we evaluate our function at these points. So this is non-periodic case. So clearly we assume that f is the function of finite support. But what is important here, so A is a fixed matrix, but A is a scaling parameter. So the bigger the A, and actually like from here you understand that if A grows, that the number of points within the unit cube, these kind of points, will be of order A to the D, just to understand for later results. So, and now we define this set that intersected from 0, 1. So this is the point, and as I already said, that this n, the cardinality will be of this order, A to the D. And here are some results. So this theorem gives us the upper bound. Again, it's formulated in that same style as we did for Fibonacci cubature formulas. So if R again is greater or equal than 2, but R is a natural number, so the 1 is excluded. So all natural numbers except 1. So there exists the constant such that the fixed volume basically, and I will reformulate this in a minute in the same way, gives us the falling bound. So again, let's look at this. This parameter is kind of, we expected that because a to the d is a number of points. So this is the number of points to the exponent minus r. So this is okay. But again, this one reminds us what we had for cubature formulas with respect to Fibonacci point sets, but this d minus 1. And this, what we can expect, like maybe optimal. But that same qualitative phenomenon that v divided by v naught. So if v of this order, and this v naught is exactly like 1 over m, so a to the minus d, then this log disappears. And the reformulation of this, as I said, but one point here, and this is important. So if you look at this corollary and what is written here, the bound is the same, but v is this fixed. But here, in addition, we got this O. So we got this O, that means we need to optimize because Fibonacci cubature formulas, they had the weights 1 over m. These are cubature formulas. They also have the same weights, but this is not 1 over m. It's close, but it's not exactly 1 over this n, and this notation is n. It's not 1 over n. So in that sense, formally, and it's by essence that these are not quasi-Monte Carlo cubature formulas. But if we consider arbitrary weights, this is allowed, then it will give us the upper bound. So if you are talking about optimization, we get this. We get this. But now dispersion. This is let me spend at least like 5 minutes maybe talking about this. So dispersion is a very simple definition for dispersion. It's very, in that sense, very simple concept, but not that easy to work with. So basically, this is the maximum volume of the box from this special class of boxes, which does not have any points from a given set T. So this is the dispersion of this set. And the lower bound for this T is very simple. Now that is clearly 1 over n plus 1, because again, you can divide this in smaller boxes and you will get that bound. And it was very interesting to get the upper bound of the infimum. So what is the optimal set, which has this lower bound, which is of order 1 over n. Again, in this formula, I do not pay attention to this, but clearly people paid attention, and this is a short list of those who worked on that and proved that this C star could be bounded in a good way. But remember that here we have optimal in the sense of decay of n quantity 1 over m. Denominator grows like n. This is optimal with respect to n. And some more results. So see, this was the result, but recently, and we will have talks by Boris Buch and Ting-Wei Chao. I think they will not only maybe cite this, but also will give us some more, some further results. But anyway, there was very interesting results which allowed, in the sense, to go from exponential dependence on D to polynomial dependence on D in an upper and lower bound. So this is very, very interesting, and I hope we will learn about this more in our today's talks. So let me skip this. It's not important. And it's just like a corollary of that. of the results for fixed volume discrepancy, we got the results for dispersion. So this is one result, and similar results we got for Fibonacci numbers. But let me formulate, and maybe we'll give a little bit an idea basically of how to get this. Let me formulate one result about the connection between fixed volume discrepancy and dispersion. So this is the proposition. It's very simple proposition. It was used before, and in particular, it is formulated explicitly and proved explicitly in our joint paper with Nastya Rubtsova, Kostya Ryutin, and myself. So this is the following observation. So if you know that dispersion of given set C is bounded from below by this V, and we had the same sense as the volume because it is a volume of the knot. Then we claim that the fixed volume V discrepancy, and this is not periodic, but periodic is even bigger. So now this discrepancy is bounded from below by this. So this kind of things are related. So, and then you know that means if you have a bound for that, then you have a bound for discrepancy, the corresponding upper bound for discrepancy. So, and let me see, maybe I have just a couple of minutes for that, but it is very easy to prove. So look at the following. So now, what is B? B here is the one which provides this law. So we can know. So for any box, we take the box, and this box is empty. So there is no intersection, and we know that the volume is bounded by that. So now we just do the integration, the numerical integration of this head function with the support on this box B. And basically this gives us the results what we need, because it is certainly bounded like this, because there was an infimum. This is bounded like this. And on the other hand, this is 0 because it is an empty box. And we get from there the bound like this. And it is easy to evaluate that integral like this is exactly this number. So we finish the proof is that. So this connection is very easy. So in that sense, in this direction is very easy. Another direction is questionable, but in this direction is very easy. So I think that I will stop at this. Yeah, because this I can stop at this point, and we have like 6 minutes for questions. Thank you very much.
Thanks a lot, Volodya, for the nice introduction and many results. Are there questions from the audience? Okay, so maybe I have one. Is there some of this fixed volume discrepancy, some particularly, say, difficult open problem or so, in the same sense as we have it for the other discrepancies? Or is it that the situation is just easier there?
No. I think we still, I mean, one question is absolutely natural, and we don't know how to solve that. That remember, in all those results, let me move back there. When we had these general results, before this, so for instance, like even like for instance in this case, for the Fibonacci, right? For the Fibonacci we have that, but we have this for r greater or equal than 2. So the question is, could we prove this for r equals 1? So we don't know. And the same with Frolov-Kubachev formulas and other stuff. So we don't know for r equals 1, because the technique which we use, we need a summation with respect to something, and that is important, that R is greater than 1, strictly greater than 1. But if R is equal to 1, that we can get like extra log, and then this would kill the whole picture. So this is one of those open problems. And other open problems, that's again for specific sets, and like that one for Korobov sets, and maybe Nastya will comment on that too, because there are some results for and really good results, comparatively recent result by Bykovsky, which give good results for discrepancy, not fixed volume discrepancy, but just discrepancy. But using that fixed volume discrepancy, we improved those results in application to dispersion just a little bit, but improved. It's better. And certainly the question is, if those results are the best possible, or maybe we can improve our results using, for instance, Bykovsky's technique. This is kind of, again, open question. So how to do that? Yeah, so basically this is...
But still the conjecture is for R equals 1, the same result holds.
I hope, yeah, the conjecture would be, yeah, my conjecture is that for R equals 1, this holds, but it will require a different technique.
Okay, thanks. Are there other questions from the audience? Okay, if not, then thanks, Volodya, again. It was a nice talk. Thank you. And we can, I think, prepare for the next talk. So I'm not a host.
Yeah, I stopped sharing.